Welcome to this presentation that introduces the proposed theory of non-finite numbers. First, we'll review some history to ground ourselves on terminology. Then we'll introduce two new axioms. The first introduced axiom is an axiom for ideal mathematics that uses for its infinity reciprocal of zero, which we can use as long as we don't use it as a rational number. We next introduce an axiom for practical mathematics that uses for its infinity Aristotle's finite potential infinity, the largest natural number so far counted to. Between the finite potential infinity and reciprocal of zero is a gap that has caused some grief in the form of holes in logic. It had previously been assumed this gap contains positive actual infinities with a property that these actual infinities are quantities of sets. Cantor proposed formality to two actual infinities by placing them in his continuum hypotheses, which is that there are no quantities between the countable actual infinity used for the quantity of integers and the uncountable actual infinity used for the quantity of real numbers. Cantor's formal structure for mathematics has been quite successful because imprecision was removed by making imprecision infinitesimal. But Cantor's formal structure for mathematics has holes in its logic. Those holes get removed by splitting mathematics in half, into ideal and into practical. This split is a refinement that puts more granularity to Cantor's mathematics. His two actual infinities get split between the two mathematics, with a countable actual infinity becoming the finite potential infinity, and with the uncountable actual infinity becoming reciprocal of zero. His continuum hypothesis remains valid after that substitution because the actual infinity that fills the gap in the proposed theory of non-finite numbers cannot be the quantity of members in a set. Rather, it is a large-scale imprecision such that it is an unspecified portion of a finite rational number. This presentation proposes a change to infinities, and infinities are the core of algebra and set theory. But I want to emphasize that Cantor and everyone associated with his work are all great mathematicians who built the foundation on which today's presentation is based. The infinity greater than finite numbers is large-scale imprecision called a local infinity. It is added to rational finite numbers to create local real numbers. The word local is because of the dependence on the value of the finite potential infinity. The local infinity, as a large scale imprecision, is evaluated statistically using finite number mathematics, and that means there is no mystery about it. And the lack of mystery means it creates no holes in logic and can apply directly to mathematical models of physics. Specifically, in this presentation, Maxwell's equations will be derived from the Dirac equation using a Lorentz transformation in which the local infinity gets added to the time-space hyperbolic angle that represents speed. And that new formatting of Maxwell's equations puts force density, the Poynting vector, and electromagnetic energy density into one mathematical model. And that is a union of empirical models we don't presently have. And that union suggests that the new mathematical model for Maxwell's equations is more fundamental. And this successful application suggests the proposed new system of numbers is correct. If you find the set of real numbers has hampered your work, and you need division by zero singularities placed in a logical mathematics without holes, then please read the textbook that introduces the proposed theory of non-finite numbers, called Special Algebra for Special Relativity, 2nd edition. 2,500 years ago, Pythagoreans were forced to acknowledge a mathematical relevance to infinity because they discovered a proof that the square root of 2 is irrational. A couple hundred years later, Aristotle wrote in a book several contemporary concepts for infinity. The infinity Aristotle thought was mathematically acceptable was the finite potential infinity, which is the temporary largest finite positive integer, what can be thought of as how far counting has gotten. Another concept for infinity Aristotle mentioned is the completed infinity, or actual infinity, which appears to have properties of being larger than the potential infinity, is positive, is integer-like in that it has no contribution after the decimal point, such that it can be a quantity of members in a set, and for a fourth property, can be added to without changing. About 2,000 years later, a little less than 500 years ago, Galileo clarified the four Aristotle properties of actual infinity by pointing out the quantity of squares of positive integers is the same as the quantity of positive integers. A couple hundred years later, Dedekind proposed the Dedekind cut, by which an irrational number is essentially the same as all numbers inside an infinitesimal interval. In his words, from now on, therefore, to every definite cut there corresponds a definite rational or irrational number, and we regard two numbers as different or unequal always and only when they correspond to essentially different cuts. Working with Dedekind and building from the Dedekind cut, Cantor further defined the actual infinity, first by giving it a name, Aleph null. Cantor then quantified the interval of the Dedekind cut as the division reciprocal of base 2 to the exponent of negative Aleph null. Cantor used Aleph null in his proposed continuum hypothesis, for which there are no numbers between Aleph null and base 2 to the exponent Aleph null, what he eventually called Aleph 1. Because there are no numbers between these two actual infinities, the first infinity, Aleph null, which is the quantity of integers, is called countable, and the second infinity, Aleph 1, which is the quantity of real numbers over any interval, is called uncountable. The continuum hypothesis effectively enforces that Aleph 1 is an actual infinity, and that means Aleph null is also an actual infinity and is not the finite potential infinity. Cantor proposed his two infinities, Aleph null and Aleph 1, over 100 years ago. And about 100 years ago, starting from Cantor's use of sets, we developed axiomatic set theory, in which, first, the axiom of infinity addresses the finite potential infinity and generally is accepted even though this counting to the potential infinity is performed by counting nothings. Second, the continuum hypothesis is effectively made into an axiom, but it leads to holes in logic. And third, axiomatic set theory was found to need the axiom of choice, which is best summarized by this example, that we can multiply two irrational numbers to a product that has the same actual infinite quantity, that is more than can be counted, of place value digits after the decimal point, as did the two irrational number factors. Mathematicians attempt to not use the axiom of choice in their proofs. The second timeline concerns the prohibition against division by zero. In a paragraph in his book, Physics, Aristotle mentioned his thought that speed was inversely proportional to density of the medium, and therefore speed was impossible in a vacuum. And that paragraph shows us the Greeks thought about division by zero. India in the 600s introduced zero as a number, which was a great achievement, but division by zero appears to have confused them, like it confuses us. Sometime between then and 1600, rational numbers were somewhat formally defined and division by zero was excluded from the set. It's also worth noting that the concept of division by zero is avoided in axiomatic set theory. In a parallel timeline, Europeans mostly used Roman numerals for numbers until around year 1200 when Fibonacci proposed the Arabic Indian numbers 0 through 9 we are familiar with today. And around year 1600 at the time of Galileo, Stevin proposed we standardize nomenclature by using decimal notation with place value digits before and after the decimal point, rather than fractions or radicals, to the benefit that real numbers became defined as the set of rational numbers plus irrational numbers. Descartes had proposed the name real numbers to contrast with imaginary or complex numbers. Year 1600 identifies a special awakening author Maurice Klein called the Age of Algebra, with Fermat and others blazing out new ideas in a world of discovery and free creation without the restraints of rigor and without a foundation of precedent. In the late 1800s, Cantor changed the meaning of real numbers so that it included his continuum hypothesis, by which real numbers of the continuum could be infinitesimally precise, with that infinitesimal precision being the division reciprocal of Aleph-1. Per that historical synopsis, there hasn't been much progress in our definition of numbers for about 100 years since the inception of axiomatic set theory. That hasn't been because we haven't been focused on it. No, quite contrarily, we've been putting exceptional effort into cleaning up the holes. It's just that we didn't find anything better, not yet. As an example of a hole, we'll attempt to prove the irrational number square root of 2 conforms to Cantor's definition of real numbers. First, to prove square root of 2 is irrational, we propose it as rational. Per the equations, we conclude as a first observation that both numerator and denominator must be even. But also as a second observation, we recognize that numerator and denominator of any number can repeatedly be divided by 2 until numerator or denominator becomes odd. This second observation is incompatible with the first observation, and we conclude square root of 2 is irrational. Now we apply Cantor's infinities to numerator and denominator. Because per Cantor there are Aleph-1 quantity of real numbers in any interval, we assume Aleph-1 numbers are in the numerator and denominator, but then we notice Aleph-1 must be even and cannot be odd because of the base of 2. And so it appears this construction fails, and square root of 2 is not in Cantor's set of real numbers. Did we mistakenly assume Aleph-1 is a finite number by assuming we should be able to divide by 2 enough times to make numerator or denominator odd? Without a consistent theory of logic, that is, logic without holes, that question cannot be answered. To formally remove the actual infinities that are quantities of a set, we'll inspect another irrational number, log to base 2 of 3. To prove log to base 2 of 3 is irrational, we see that base 2 to exponent p is even, and therefore cannot equal odd number base 3 to exponent q. Notice that p and q could equal 0 in that last equation, because base 2 to exponent 0 equals base 3 to exponent 0, which equals 1. P and q equal to 0 satisfies the equation 0 equals 0 times log to base 2 of 3. But if we venture to let p and q equal 0, then in the parallel equation development, we are forced to accept p and q both equal to the division reciprocal of 0. We have a rule in the definition of rational numbers that division by 0 is prohibited, and therefore a division reciprocal of 0 is an irrational number. The two irrational numbers, division reciprocal of 0 and log to base 2 of 3, are related, it appears, by the equation division reciprocal of 0 equals division reciprocal of 0 times log to base 2 of 3. If we suppose the division reciprocal of 0 is integer-like and that it has no contribution after the decimal point, so that it can be the quantity of a set, then that equation states that the division reciprocal of 0 is the smallest number we can multiply into irrational number log to base 2 of 3, so that there is no contribution after the decimal point in the product. By making division reciprocal of 0 an irrational number, we are no longer shying away from it. Division reciprocal of 0 is both positive and negative because of the 0 in the denominator. A second property is that division reciprocal of 0 is the largest magnitude of numbers. To formally accept these two properties, along with the calculations using addition, multiplication, and exponent, we propose a new axiom of reciprocal of 0, for which no calculation that includes a division by 0 can equal a non-zero finite number. The proposed axiom means we cannot have 0 divided by 0 or reciprocal of 0 subtracted from reciprocal of 0, and that is less restrictive than the old rule of completely prohibiting division by 0. Next, to prove actual infinities that are a quantity in a set must be discarded, we recognize Cantor's infinity for real numbers, called Aleph-1, is positive, and that means it is too small, such that Aleph-1 multiplied by log to base 2 of 3 has a result that includes a contribution after the decimal point, and therefore cannot equal Aleph-1. What was just presented was a proof that an actual infinity that is a quantity for a set is not a mathematical entity, and perhaps a claim can be made that a proof cannot pertain to something that does not exist. Regardless, we've drawn that conclusion and we will go with it, assuming it's correct. We reach the conclusion that an actual infinity that is a quantity of members in a set does not exist after we formally recognized all the place value digits in log to base 2 of 3 by use of the proposed new axiom for reciprocal of 0, by which we can now use reciprocal of 0 in calculations. In support of Cantor, his continuum hypothesis holds true if we replace Aleph 1 with reciprocal of 0 and we replace Aleph null with a potential infinity, because after those substitutions, the continuum hypothesis states there are no actual infinities that are a quantity of members in a set between those two numbers. Returning to the square root of 2, we recognize that the division reciprocal of 0 is both even and odd, so that we can replace square root of 2 into the equation reciprocal of 0 equals reciprocal of 0 multiplied by square root of 2. Referring back to the Dedekind cut, we have made the cut a scissors cut with the irrational number on both the high and low sides of the cut. The cut is now an interval of integer 0, not infinitesimal, and we no longer need Dedekind's word essentially. We've rewritten Cantor's continuum. We have rewritten Cantor's continuum hypotheses, but we do so without insult because we are climbing on the shoulders of giants, and we thank Cantor specifically for the foundation he has built for us. To further understand the Dedekind cut being changed to a scissors cut, we look at the irrational number natural log of 2. Start with the summation of reciprocal positive integers and then divide its terms by 2 and subtract that summation from the original summation twice to a result of 0. The resulting summation has two parts. The first part is recognized as a summation series for the natural log of 2, but also there is a second part which must also equal natural log of 2, and it is a summation of terms each of which is integer 0. You can substitute a large number for 1 over 0 to show the validity of the second part equaling natural log of 2. Go back to the original summation equation for t. Note that the last term has a value equal to integer 0 because 1 subtracted from reciprocal of 0 equals reciprocal of 0, and its reciprocal is 0. That last term remains equal to 0 if we increase the value of reciprocal of 0 by doubling it and adding 7. Per that example, the first natural log of 2 summation equation can have the quantity of terms increased and increased substantially for more place value digits after the decimal point, but with those place value digits each having a value of integer 0. That's how an irrational number has no end to its place value digits and can be both high and low sides of a Dedekind cut, with a Dedekind cut an interval of integer 0. We now split numbers between ideal and practical. Ideally, an irrational number has place value digits after the decimal point that have integer 0 contribution, as was just described. We inspected irrational numbers ideally and hypothetically and introduced a proposed new axiom so that the positive actual infinity, specifically Aleph 1 proposed by Cantor, could be proven incorrect and replaced by reciprocal of 0. Now we revert to what is practical in our real physical, natural, geometric world. There is no division by 0 in our real world. And we've proven there is no positive actual infinity. That leaves only the finite. As another axiom, we propose that all quantities in a real world are finite and rational. A number, for example, angle of 45 degrees, is only a rational number, and when expressed in radians, has only finite precision, not the ideal precision of a rational number pi over 4. Because of the finite precision, a quantity also has finite imprecision, which is the non-finite exciting part and will be discussed next. In the real world, a physical value that is an irrational number is limited to a finite count of known place value digits after the decimal point, and the place value digits are unknown and unknowable after that count. The split between a physical reality and an ideal perfection is a split between applied mathematics and hypothetical mathematics. Another property of that split is that in applied mathematics, the finite count increases in time. It appears that Cantor and his predecessors created mathematics around a positive actual infinity that straddled the proposed two forms of mathematics, ideal and practical, and was a combination of the two of them. And the proposed theory of non-finite numbers is a refinement of Cantor's work for better granularity. Without Cantor's positive actual infinity, we no longer have real numbers. What will be proposed to replace real numbers are called local real numbers. The word local refers to a local value of the potential infinity, which is a finite number that represents as far as counting has occurred. The potential infinity has the symbol Lmax for maximum large number. To illustrate the time dependency of Lmax, we can say that in the past Lmax was smaller, now we have Lmax, and in the future Lmax will be larger. Time is an aspect of physics, and the time dependency on the value of Lmax shows that applied mathematics and physics are coupled. Use base 2 to construct a local real number. The known portion of the local real number is a rational number that is called a truncated number. A truncated number has a maximum of potential and infinity Lmax place value digits, which are limited to ones and zeros because we use base 2, both before and after the decimal point. For Lmax equal to 0, which perhaps models the beginning of time, the truncated numbers are 1, 0, and -1. For Lmax equal to 1, there are 9 truncated numbers as listed, spanning from -2 to 2. For Lmax equal to 2, there are 33 truncated numbers. For Lmax equal to 3, the span from 0 to 1 is given. To address place value digits that are beyond a count of Lmax, before and after the decimal point, we recognize those place value digits are unknown and unknowable. These unknown and unknowable place value digits from Lmax plus 1 all the way to division reciprocal of 0 are given the symbol D. The string of D's starting at a count of Lmax plus 1 after the decimal point is called a local zero. A local zero is the small-scale finite imprecision of a local real number. D is the difference B minus B. Each B is a 0 or a 1, with the selection unknown and unknowable. B means both, or B means box, in reference to Schrodinger's cat, which has state 0 alive and state 1 dead, with a selection unknown and unknowable until the box is opened and an observation is made. Each B is independent of each other B. Per that construction, each D is a -1, a 0, or a +1. For nomenclature, 3 dots is the same as Lmax and represents what has been counted to. Symbol 6 dots is the same as reciprocal of 0 and is beyond what has been counted to. To visualize 6 dots, take an irrational number like square root of 2 and truncate it at the decimal point to discard everything except the initial integer 1. We created this integer 1 by a bulk operation called truncation, and we did not address each place value digit one at a time, which would have required counting. Therefore, symbol 6 dots means counting has not yet been done, and mathematical processing requires a bulk operation. For the large scale, which is before the decimal point, it is difficult to visualize the meaning of the string of D's. And further work suggests the large scale imprecision is the division reciprocal of the small scale imprecision. Regardless of using the division reciprocal or not, large scale imprecision is greater in magnitude than base 2 to Lmax. And per our selection of using D's rather than B's is both positive and negative. The large scale imprecision is not a finite number and therefore is a form of infinity. And we will call it a local infinity with a prefix local applicable because it is dependent on the value of Lmax. And note that the local infinity cannot be the quantity of members in a set. To help visualize a local infinity, Imagine an angle of 45 degrees expressed in radians as pi over 4. That value of pi over 4 is accurate only to Lmax place value digits after the decimal point, after which is some trivial, negligibly small imprecision. But before the decimal point, the long string of zeros only extends to Lmax in quantity, and beyond that, there is the possibility of some ones, and more generally, some negative ones. When we apply this new number system called local real numbers to mathematical models of physics, a unitless number like an angle must include these unknown and unknowable large-scale place value digits of the local infinity. Note that there is no mystery in the local infinity. This is a very important property of local real numbers, and so we'll point out why there is no mystery. Known or knowable place value digits are limited to a finite quantity, so there's no mystery there. Beyond what has been counted, place value digits are unknown and unknowable, and are specified to be Schrodinger's cat boxes. We know these boxes from physics, so there's no mystery there. Local infinity is constructed from one or more unknown and unknowable place value digits, and although we don't yet specify if it is simply digits, is reciprocal of a local zero, or is positive rather than positive/negative, we know what these options are and can use statistical methods, so no mystery with a local infinity. The lack of mystery around the local infinity is maybe because we are not forcing it to be a quantity of numbers in a set. And without known or knowable place value digits beyond what can be counted, the mysterious axiom of choice is not needed when using local real numbers. The proposed theory of non-finite numbers has no mystery. We expect no inconsistencies or holes, no paradox or deviation of mathematics from logic. Therefore, we can apply the local infinity to applied mathematics. The second axiom, what switched mathematics from hypothetical to applied, means we switch our mindset from intangible to practical. We ground ourselves in physics and measurements taken, so that our theory of mathematics is based in reality. And evidence to support an argument on the structure of our theory of mathematics can be verified by independently performed experiments. Now that we have an infinity based in logic, we can apply it to division by zero singularities that occur in mathematical models of physics. We start simple. Our first example application is location and momentum of an electron particle. The electron particle moves at speed v equal to speed of light multiplied by the hyperbolic tangent of a hyperbolic angle alpha. The subscript m means angle alpha is a truncated number. In a mathematical expression, energy and momentum, respectively, are combined using a Pauli spin matrix q sub x inside an exponential function. Same with time and location space. Small scale and large scale imprecision are added to the truncated number hyperbolic angle alpha using a Lorentz transformation in which the m subscript changes to an s subscript. A Lorentz transformation is an addition of a hyperbolic angle. The angle that gets added has a 1 minus q sub x term that keeps the result finite and applies because rest mass and time are also constructed from a unitless hyperbolic angle inside an exponential function. Adding small scale imprecision is trivial because small scale imprecision is nearly zero, and there is no change to energy, momentum, time, or space location. The small scale imprecision Lorentz transformation models the original electron particle. Adding the positive large scale imprecision results in energy equals momentum and time equals space location, and therefore models a photon particle. We conclude that by changing our number system from real numbers to local real numbers, what had been a mathematical model of physics for an electron particle is now a mathematical model for a combined electron and photon particle, such that the photon is a projection of the electron that emitted it. An electron is modeled as a wave in the Dirac equation, and the same Lorentz transformation for adding large scale and precision results in Maxwell's equations, which models wave dynamics of a photon. Details are in the textbook, and I'll flash the busy equations on the screen. This is the Dirac equation written as a math person would write it. The four Dirac spinor components are in the psi column vector on the lower right. This is the Dirac equation written for mass and electric charge equal to 0, and with a column vector of zeros on the right replaced with non-zero quantities. This is the Dirac equation for the large scale and precision. This is the same Dirac equation for large scale and precision, but with electric and magnetic field components substituted into the Dirac spinor, and with electric current density components substituted into the right spinor. The Pauli spin matrices correspond to X, Y, and Z, but uniquely so. And for a complete mathematical model of electromagnetic fields, all three rotations of Pauli spin matrices are needed. This is the last rotation of the Pauli spin matrices of the Dirac equation. The Dirac equation is a wave equation. We do not directly measure waves, but rather we measure particle properties formed by multiplying spinor components by other spinor components. For the Dirac equation for the electron, spinor components multiplied by spinor components equals the four components of electric current density. For the Dirac equation for the photon, presented here, spinor components multiplied by spinor components equals the 8 components of the electromagnetic force density. Two more of the 8, two more of the 8, and the last two of the 8. The 8 force density components can be arranged into an equation of cross products and dot products. It looks messy, but it is clean in that no negatives had to be artificially inserted. This equation is critical in substantiating the validity of the Dirac equation form of Maxwell's equations. Details are in the textbook. In summary, the Dirac equation has a result that is Dirac spinor components in a column vector written with psi symbols. These spinor components are multiplied by each other to form an electric current density, which is what is measured. The same mathematical process used to calculate electric current density is used after the Lorentz transformation of the Dirac equation that applied the large scale and precision. And instead of electric current density, what results is the measured electromagnetic force density. Included in the force density is the Poynting vector and electromagnetic energy density. Force density, the Poynting vector, and electromagnetic energy density are currently separate, empirically discovered mathematical models of physics. They have not before been placed into one mathematical model of physics. Therefore, applying local real numbers to the Dirac equation has resulted in a more comprehensive theory of physics for electromagnetism than what was available before the proposed theory of non-finite numbers. Because of this application, we conclude real numbers defined per Cantor's continuum hypotheses do not exist, and local real numbers defined per the proposed axiom of reciprocal is 0 and the proposed axiom of only finite numbers in applied reality do exist. Electromagnetism is a 100-year-old theory, and the Dirac equation is almost as old. A new understanding of these old theories using local real numbers is interesting, but more exciting will be applications of local real numbers on more modern or in development theories of physics. The next singularities to be analyzed are the center of a black hole and the relationship between quarks and gluons. And the proposed change to electromagnetic theory presented today might let us get perturbation theory out of QED. And after that, the next phase of physics is not a grand unified theory, I don't think, but rather is getting outside our universe by identifying the computer-like memory register that stores truncated numbers, because it appears these numbers are more fundamental than the materials and forces that make up the stuff of our physical universe. Pythagoras was first to suggest the world is numbers and not stuff, and I think he'll be proven correct. I want to thank Nicholas Gisson, a professor in Geneva who specializes in intuitionist mathematics. Per a Quantum magazine article written by Natalie, Nicholas suspected there was a coupling of intuitionist math with time. He inspired me to make this video, not so much because he himself has nice videos, but because I was unable to explain my proposed theory to him as concisely as I wanted to. My connection to him was initiated by a tweet from Quantum magazine, probably initiated by Natalie Wolkover, who appears to be the world's clearinghouse person for newly developing concepts in mathematics and physics. With regard to my own credibility, I have no credentials because I'm not a mathematician nor a physicist. I'm a turbine engineer. Applied math is only a hobby. Because I am outside of academia, I have no idea how to publish a technical paper. Because I don't know any other means of publishing, I wrote the proposed math given in this presentation in a textbook, self-published on Amazon. Special Algebra for Special Relativity, 2nd edition. It's available for only $20. Theory on infinity, developed for that textbook, but inappropriate for a textbook, was given a shell of a story and placed into the book Alien Invasion Math Story. And I've recently published a sci-fi novel, Her Wants and Needs. The protagonist is an engineer. If you listen to this whole video, then you will likely enjoy all 3 books. I do. You can follow me on Twitter. I look forward to some discussion. Thank you for your time.